GoDB yesterday. He gave a really good introduction about graphs. So I'm just going to super quick one. I live in a world where data is connected, where we see no record standing alone, and where we see the value of connections. In this case, I have a very romantic view of the world. Anne loves Dan. Sadly, does not imply the reverse. That's very sad, isn't it? But if we wanted to store and capture that in Neo4j, we could create a piece of query language syntax. And we take the pattern that we're interested in, Anne loves Dan, we would encode it in ASCII art. So we've got, right, you're going to like this. Ooh, gadget. We have an ASCII representation of a node with some data in it. We have an outbound relationship modeled on Visio, loves to another relationship which represents a person who has name Dan. And we can put that inside Neo4j, and we could do that many times, and in the end would lead to something like a social graph. So you could build up from these very small atoms, build quite sophisticated and interesting nets like Twitter, Facebook, LinkedIn, what have you. And then you can start to ask queries of that data. You can start to ask, who does whom, get my English right, whom does Dan love? Whom does Anne love? And in this case, we'd find out that Anne loves Dan. And hopefully, because we're romantic, we'd discover that Dan reciprocates. Wouldn't that just be lovely? As it is, with computer people, it's typically never the case, is it? Yeah. The sad loneliness of the computing practitioner right there in graph form. The day will come, people. All right, cool. So if you're going to build large production systems of graphs, and many of us are doing that nowadays, graphs, I think, have kind of tipped past their inflection point. They're quite part of our everyday vocabulary now. Many of us are building graph-based systems for real in our businesses. But in order to have confidence that we have a dependable system, we need to introduce clusters. We need to introduce redundancy. Why? So that we can have high throughput. You know, one machine has to logically serialize requests, have many machines, you can parallelize requests. Why? Well, for redundancy. If I've only got one copy of data and it's on fire, I lose service. If I've got multiple copies of data and one of them's on fire, I don't lose service. For availability, if I have one machine and it goes down, my app experiences 503 server error, no availability from the point of view of the application. If I've got lots of copies and one goes down, I can switch over to another and maintain service. Now, in Neo4j, we've been working on this stuff for years. We're working on Neo4j 3 at the moment, so we've had 3 methods of building this. In Neo4j 3.1 onwards, we have a very novel network architecture that supports this, called causal clustering. And this is where I will be talking today. One thing, though, when you've got a cluster, things get difficult. When you've got a cluster, this kind of model that computers, that I can read, I can write something into memory and then subsequently read it back, that vanishes. In a cluster, you've got multiple threads, potentially owned by multiple different parties, multiple different apps or instances of an app. And you've got this thing called time, right? And time is evil. I mean, not only does it age us to this withered form that you see before you. I'm only 23, but you know, distributed systems will do this to a human. But reasoning about it, it's really hard in distributed computing. So there's no free lunch. And wanting a good consistency model in a cluster makes things tricky. Now here's the motivating problem for consistency. So I have an app, and I need to log in to make my purchase. But actually, I haven't got a login on this system, so I'm going to create an account. I create my account, get redirected back to the login page, try to log in, put in my username and password, and then, oh. Has anyone seen this? Yeah, we've all seen this, right? It's really irritating. On a web browser, it's not so bad, because you kind of, Control F5 or Command R if you're rich. That's what it means. I am rich, Command R, Command rich. irritating is this? So, but you know how to fix this, right? What you do is you time how long it takes by repeatedly refreshing, and then you do thread.sleep 5,000. Problem solved, right? No, of course not. That's a terrible idea. So in Neo4j, we want to fix this because we want it so that not only can you have a cluster that's scalable for volume and redundancy, but we then want to take the pain out of working with a cluster, because clusters are hard. They're not macho. Some people have got this idea that clusters are important and macho and make you feel brave because you use them. I think the appropriate response to a cluster is to be terrified, right? Because they are really hard to reason about. So we want to take away that terror from using clusters. So we have this idea of splitting the roles. Now, all of this work is done within the constraints of FLP. So many of you know CAP. This is an older magic than CAP. And Fisher, Lynch, and Patterson tell us that there is a trade-off in any distributed system between availability, that is the property of a system where it can give an answer, even if that answer is wrong, versus reliability, which is the property of a system to give the correct answer. And you can't have both, right? So, for example, that does mean, unfortunately, you can't, in theory, have a system that does exactly once guaranteed end-to-end delivery of messages, right? Even though some people mistakenly claim that. So you've got this tension, and you have to choose between them. You have to pick your part on that spectrum. In Neo4j, we tend towards the reliability end. In a pathological case, we would prefer to become read-only, to become unavailable from CAP's point of view, than to give a wrong answer. We think giving a user a database a wrong answer is kind of crazy, right? You don't want people to lie to you. I mean, we do have politicians, of course. I live in the UK, so I know all about lying politicians. So we've split our cluster into two roles. We took our inspiration from the web. In the web, you would typically have a small number of app servers that do the clever stuff, and a large number of things like reverse proxies and caches and so on that tackle the kind of muscular, voluminous workload. So we split our cluster into two roles. The core roles are for data safety. They are a small number of machines, 5, 10, 3, 12, whatever, but not 100 or 1,000, whose job is to keep your data safe, to keep it sufficiently redundant, so even if there are failures, still reads and writes to that data. Writing into the core is super easy. You spin up your Neo4j driver in your preferred language, and you send some Cypher Neo4j query language using that driver over to the core cluster. One of the machines that receives that network message will then try to logically broadcast it to the other machines, and when enough of those other machines have accepted the message, then we can safely assume it is written. And at some point later, those machines will also sync. The reason that we have this nice majority protocol, we know it's safe once a majority have responded, is because this is all built on Raft. It was built out of Neo4j's London lab, hence the skyline there. So the Raft protocol is really nice. Most distributed system protocols are really difficult. Many of you may have read things like Paxos. And I have a PhD, and I found Paxos tough. I'm an actual computer scientist, and Paxos made me tear my hair out, which is why I've got this crap haircut. Actually, what's lovely about Raft is that it achieves many of the same goals as Paxos, but it's humane, it's easy to understand. It's an algorithm designed with its primary goal to be understandable by humans. And that's important when you're building distributed systems, because complexity is where bugs hide, and a bug in a distributed system is amplified, right? It can do unpredictable things across processes, across machines, across the globe, and they're really tricky to figure out. Raft, on the other hand, is designed to be easy to understand, and it has only one goal. And its goal is to keep logs on different machines tied together. It took me 2 years to figure out why it's called Raft. It's because it is logs tied together. 2 years, seriously. I even know the guy that built Raft, and I didn't figure it out. That's how smart I'm not. So the Raft protocol is really nice, right? So in this animation, what you can see here are 5 machines collaborating via Raft. And what they're doing is, at any given moment, one of these machines is playing the role of leader, and it has the job of deciding ordering, A before B or B before A. So as transactions, as state changes are coming in, it's appending to its log, and then it's asking other members of the cluster to append entries to its log as well. So say, hey, come on, you guys, I've just appended number 5 at position 10. Can you guys do that? And you guys will look through your logs and say, yep, I agree that I can put number 5 in position 10, and then you let me know. If the leader dies while it's doing its thing, that's okay. Someone else can take over as leader, because it turns out everyone else has the same log, everyone else has the same history, that the person that's most up to date, or coin costs, if several people are up to date, can simply take over and keep running. So Raft has this really nice property that it's a non-blocking consensus protocol. Even in the event of failures, we can pick up and carry on from where we left off relatively quickly. Typically, as soon as a heartbeat has been missed, an election will happen, and the cluster continues with very little panic, in fact, zero panic and very little sweat. So in a nutshell, Raft's job is to keep logs together. The log contains both the values that your application cares about, or in our case, records that ultimately end up in the database, but it also contains the membership history of the cluster. So from Raft, we have an view. Am I getting boring? They're cutting me off at the back. Hello. Come on, some interesting stuff coming, bear with me. So if we ever need to understand who's participating in the cluster, that's implicitly part of the log as well. So we have all of the history of the whole distributed system going back, in principle, to time equals 0. That's very helpful. Entries are appended to Raft logs and subsequently considered committed if a majority of participants agree. Raft does everything on majority. There are more efficient quorum styles available, row quorums, tree quorums, and so on. But these have, the trade-off for those is, although you need only a minority of the cluster to agree, they have much more intricate recovery semantics. They have much more intricate voting semantics for that. Raft goes simple. If a majority agree, n over 2 plus 1 agree, then we go for it. This actually does stop things like split brain. If you can't get a majority, you can't elect a new leader, so you can't get split brain in the cluster. It's very, very cool. So the implication of this is that the majority agree with the log as proposed, which means that the majority have a complete and accurate view of the system from time equals 0. Raft is absolutely lovely. Now, appended entries can be removed. Yeah, just because I append onto the end of my Raft log doesn't mean that entry is safe. But we never, in Neo4j, acknowledge the transaction in the appended state. We only acknowledge once it's moved to committed. So one slight tweak of Raft is that things at the head of the log aren't necessarily going to stay there, and we'll see why momentarily. So this is how Neo works. We have a Raft log, which ultimately pushes stuff into the underlying database log, and then it gets applied to the graph. Things on the left here, so you can see here that these logs don't always disagree with each other. And some of these things, in fact, these two purple entries, may actually be removed from the log because they disagree with the majority here. So what's going to happen is Raft is going to notice that these guys are different from the majority. These guys will drop these appended entries, and they will ultimately move on to committing the same history as the majority. Again, it's majority-driven, very, very straightforward. And this percolates through, gets into the graph where all the real fun action for users of Neo4j happen. So core is a small group of Raft protocol, Raft members effectively. Read replicas are for query throughput. They are how to take manage enormous load in your Neo4j cluster. They are fully fledged Neo4j instances, but they do not participate in the Raft. In fact, they use an asynchronous log shipping mechanism, kind of Kafka-ish in a way, in order to stay up to date with respect to the core machines. I said asynchronous. I mean, you should be worried by this, right? Because at the beginning of this talk, I was like, hey, I'm going to show you how we can make a cluster that behaves as if it was a single value for reads and writes. And now I'm saying things like Raft log is not always consistent and asynchronous. You should be like, does this guy know what he's talking about? This feels bad, asynchronous, this is worrying, this is thread.sleep all over again. Hold that thought. So if you want to get stuff into the read replicas, you first write them into the core group, and then those logs get shipped down to the read replicas. And those read replicas are topology aware, so they know which data center you've got them deployed in, and all of that good stuff. The drivers and the cluster topology know about one another, so the drivers do clever routing based on whether you're reading or writing, and where you are in the world. That's all very nice and very, very seamless. What we want to do in order to scale out is direct most of our read load at these replicas, because they're multiple, they're cheap. These can be deployed in tens, hundreds, thousands, tens of thousands, I don't care. Deploy them as you see fit, because they place very little load on the core servers. Now, the reason that we can do this kind of split between reads and writes in a graph is that in a graph, even when you're going to write, you typically have to do some read work first. You typically have to traverse through the graph or pattern match through the graph to find the target where you're ultimately going to do a write, where you're going to add a node, add a bit of structure, change some properties or whatever. So we observe kind of an 80-20 rule at play here, that in a graph workload, 80% of it is reads and only about 20% of it is writes. So this split makes a bunch of sense for us. It means that you can spin up quite large clusters and allow the infrastructure to take the load for you. How do we build it? Well, this is where the computer science stuff meets contemporary software engineering. So, in Neo4j, a typical app looks like this. Well, I could be an architect, right? That's a proper architect level picture. Yes, I've done the intellectual work. Now you low-level developers just go and implement my vision. Sorry, architects. Sorry. But the developers already know, by the way. They know, they're onto you. But it looks a bit like this. So you've got some app server, and then there's a driver, and the driver talks something called the Bolt protocol to Neo4j. Now, if we dig down a bit further, if you want to install some of these drivers, it's easy peasy to do it in your language. They're well supported, blah, blah, blah. You don't need to worry so much about that. It's as easy as installing a JDBC driver. Plenty of guides on our website about how to do it. Literally in code, this is Java. Don't get freaked out. I'm not going to put too many curly braces in front of you. This is Java. If I wanted to connect directly to a machine, I would use the Bolt URI scheme, and I'd say graph database.driver, Bolt, and then the target server. That's the way I kind of do a straightforward client-server interaction. But you can actually do this. You can use the Bolt plus routing scheme, and you could connect to any of the core servers. And that Bolt plus routing scheme has the nice side effect that it actually is cluster aware. So connecting via this scheme will mean that your driver in your app has now got a view about the cluster and can start to make some routing decisions on your behalf based on the workload you throw at it, based on the data center that you're nearest to, based on your read-write mix and so on, which is kind of cool. So here would be, again, a kind of global architecture, several users using apps through the app servers, talking happily to the core and read replica machines. In Java land, it's pretty straightforward. If you know that you want to write something, you set up a session so that it has access mode write, and then you do your cipher work here. And unsurprisingly, if you're going to do read, you set up access mode read. And the drivers do some routing decisions for you. As it turns out, under the covers, there's also a bunch of stuff using some of the topology metadata that we have, so the driver will pick what it thinks is the best machine for you to talk to at this point in time. But still, we have this issue. Can you read what you write? This is appalling, right? This is. I've got to tell you something. I know I've only got like 10 minutes left, but sometimes my mum, who's lovely, asks me what I do for a living, and I say, oh, Mum, I've got this really important job. I make sure that when you write something into a computer, you can read it. And she's so unimpressed. She's like, oh, right, that sounds so important. Well done, son. I'm really glad that we invested so much in your education. That's great. Yeah, I'll tell all the family, right? But actually, obviously I don't correct my mum. That would be terribly rude. But in computing, it's really hard in a distributed system to read what you've written, right? It's really difficult. We sort of went through a phase a few years ago where we gave up, right? and we branded that eventual consistency. And then because we had a nice idiom for it, we had a name for it, like, yeah, we know that's a problem, but we've named it, so we'll get around to solving that at some point. We did kind of give up. We were in this world, right? You know, kind of this world of pain where we Fred sleeps. It turns out, though, even in strongly consistent systems like Raft, it's okay. There's never, if you were like, you know, a deity looking down on this system, you could see that there is never perfect consistency. The speed of light limits the level of consistency we can have, right? Messages take time to travel. So even in my wonderful Raft system, there can still be situations where some levels of the log are ahead of others. So if I query this server for, you know, this green node here, I'm going to see it. But if I query these servers for that green node, I'm not going to see it. Again, are you worried? Because I'm kind of claiming that we've solved this. This looks desperately worrying. Even in this amazing Raft-based system, this doesn't seem to work. This is normal behavior, though. The point where this becomes problematic is if all of this low-level machinery that I care about and my mother doesn't is surfaced to you as application developers. Because it turns out you guys have got a day job to do, right? Which is like delivering app functionality, system functionality to your end users, to customers, to business users, and so on. And so often recently in database systems, we've been like, hey, here's a bunch of complexity that we haven't been able to solve. Enjoy. And some of you have been like, wow, this is so much fun computer science. And some of you have been like, God damn, I've got a day job to do. Well, I'm going back to Oracle, man. This is too hard. And if we're in this situation where we create a username, and then we try and log in, and then we get retry, yay, thread.sleep. That's the most prevalent technique in distributed systems. Why didn't this work? It was because of eventual consistency, or moreover, because we surfaced the semantics of eventual consistency up to the app level. And that's a mistake, right? We can do better than that, or at least we should be able to do better than that. So let's try this again. Here's our Neo4j cluster with some core members and some read replicas, and I'm going to create an account, and I get the Raft machinery happening, and eventually a majority of those machines agree, and I respond that the account is created. Note, if you hit this machine or these machines at this point, no account. Worrying. So then I go over here, I need to log in, so I type in my new username and password. If you're wondering, the password is password. Password, that's right. It's another distributed system secret. All passwords are password 123. Notice in the background here, some stuff's happening, all good. Here, though, I try and log in. I hit this read replica down here. What's going to happen? Epic fail in front of an audience of people that I can barely see, but are now thinking this guy is losing my credit by the moment. Okay, give me one more chance. We can do better. It turns out that in most sensible databases, you have versions or transaction IDs or something like that. Some view, something that you can hook a write against. In Neo4j, it is transactions. Neo4j is an ACID transactional database. And it turns out that our transaction identifiers are strictly monotonic integers. 1, 2, 3, 4, 5, a million and one, a million, blah, blah, blah. It turns out that the really nice thing about integers, it's, even you computer scientists have enough mathematics for this. You know which are bigger and which are smaller, right? Yeah. I'm not asking you to do any crazy discrete math, just is this number bigger, is this number smaller? We can use this to create a kind of bookmark. It's not really like a bookmark, it's a terrible name, because a bookmark you can go back to a bookmark. You can't really go back, so it's not a bookmark, it's just a crap name. But then we're called Neo4j, so we know all about crap names. Let's try again using causal consistency. So this bookmark feature allows us to specify a point in time, a transaction, a version, if you will, beyond which we don't want to look. We never want to go back in time, only forwards. So now we can create an account. Here we go, creating the account here, and the Raft machinery kicks in lovely, and the graphs are getting updated. A majority has accepted this, so it's become committed. We return to the user. But this time, look, we've got these things, these bookmarks. They're effectively Neo4j transaction IDs. Now, if you carry that bookmark through the client, maybe you round trip it through the URI or the cookie, or maybe you're kind of crazy enough to persist that as mid-tier state in your app server. Don't do that, it's a bad idea. But some of you will do that. Now, as long as you supply that session, that bookmark back, Watch what happens now. Of course, these things are still replicating on the right-hand side. I'm going to try and log in with a particular user. This time, it doesn't fail. But it's like, oh, actually, you were waiting for transaction ID 11, and I've only processed 10 through my asynchronous log shipping. Hold off a sec. I'm just going to kind of wait for that transaction to process, and we wait, and the transaction propagates, and then we serve the transaction, and boom, login successful. That's actually not a million miles away from thread.sleep if you think about it, except the database knows when a transaction has been processed, so it knows when it's safe to run your new login query. Rather than guessing, leaving that as an exercise to you guys, is it thread.sleep 5,000 or thread.sleep 8,000 or thread.sleep 1, I don't know. We're actually able to do this. So when the database is ready to accept your query, it will run. If the database had already processed in advance of your transaction, your query would run immediately. So we're handling this for you. You'll never get to go back in time. You never get the situation where you created an account, and then just because of the vagaries of distributed systems, you went to a replica that didn't have that record, and your account didn't look like it didn't exist. You'll never get that. You'll never go back in time. So this is causal consistency. It's quite a strong guarantee. It's not quite at the strongest end of the spectrum, at linearizable or so on, but it's way, way stronger than eventual consistency, which is a euphemism for good luck, everybody. That's what it means, eventual consistency, good luck, everybody. It's actually way stronger than that. It means that you as a user can reason about this database very comfortably. It's like using this mechanism, I can always read at least what I've written. The guarantee is I'll never go back in time, which makes the database cluster very easy to reason about. From your point of view as people who are charged with delivering systems, using this idiom, this abstraction, means that you have to worry about your domain problems, not how long do I thread.sleep for. So if you want to do this, it's very, very easy. You open a session as per usual. When you run your transaction, you'll get, when you open your session, you can ask for its last bookmark, which will be, in this case, the results of running this transaction. And then you can use that bookmark, round trip it through your client, whatever, store it in your mid-tier, please don't. As long as you present it back to the database next time around, then you're going to get this wonderful no back in time semantics. So obtain a bookmark. You want to use a bookmark, you just have to pass the bookmark value, whoops, thank you, into your begin transaction so that when you use it next time around, the bookmark's in there. That was a bit of Java code. Don't worry, the same exists in more human languages like Python, for example, and it just works out of the box for you. So, being the extremely respectful and well-behaved presenter that I am, I've now come in at my 30 minutes. I'm happy to take questions from the audience for a few minutes, and I'll be around all day, so if you've got things you don't want to ask me in front of a room full of strangers in the dark, which is admittedly a weird setting, then please just come and grab me, and I'm happy to chat with you. Thanks, everybody.